Good morning, everyone. So today I'm going to cover basically two topics. A short introduction on big data, what exactly big data is, and then we'll talk about one of the big data technologies, Spark. Since I have only 20 minutes, I won't be able to go into a lot of depth, but I'll be around, so if you have questions later on, just grab me and I'll be happy to answer any questions you have. So before we jump into the presentation, a quick summary about myself. I'm working at a startup called Glassbeam, and I have a dual role there. I'm the principal architect for all the analytics and the machine learning components that we built, and I'm also the engineering manager for one of the products that we are building. Prior to this, I've worked for a bunch of startups, including two of my own, and my passion is basically building new products, machine learning, and big data analytics. I also wrote a book on big data analytics with Spark. It was published earlier this year, and it basically guides you through different kind of analytics that you can do with Spark. It has a lot of examples. It also includes a primer on Scala for people who are not familiar with Scala, and it also covers some of the other big data technologies that typically people use with Scala or with Spark. A quick overview of Glassbeam. So we are a SaaS product company. We are not a consulting company, and our product basically ingests multi-structured data from any kind of machine, any device out there, and allows our customers to do analytics on it. All right, so let's talk about big data now. So as most of you know, data has been growing at a very exponential rate over the last several years. And so where is all this data coming from? A small chunk of that data is basically the traditional enterprise applications. So applications like CRM applications, ERP applications, website activity tracking applications, right? Some of that data is basically coming through the traditional corporate applications that most businesses have. The next big source is social media, which includes basically apps like Facebook, Twitter, LinkedIn, Pinterest, and as I'm sure everybody in this room is using one of them. Probably more than one, right? So people are constantly posting updates, posting videos, posting pictures. So that's a big source of data that has basically we have been gathering over the last several years. But the biggest growth is coming from this thing called Internet of Things. So almost 40% of the data today is basically from IoT devices. So what exactly is IoT? It's basically a network of devices that are embedded with software for collecting data and sending it over the internet. So this is not just devices that allow you to access the internet, but they're actually instrumented to collect data about how exactly that device is getting used, what exactly you're doing with that device. So one example of that device is the smartphone that we all carry. So there's huge amount of data that Apple, if you're carrying iPhone, for example, Apple is capturing in terms of how exactly that device is getting used. Same thing with smartwatches or anything that has the label smart typically is basically capturing a lot of data in terms of how that device is getting used. And typically the product manufacturers using that data for a lot of different uses, but the end goal is to make the user experience much better. And according to some estimates that there will be 5 times more of these devices than humans by 2020. A subset of IoT is industrial IoT. So these are basically devices that are a lot more complex, that provide a lot more complex functionality and generally a lot more expensive, but they also generate a lot more data. I've shown some examples here. So this includes modern manufacturing equipments, automotive equipments, medical equipment that you see in labs and hospitals, data center devices. And just to give us an example, typical flight, right? A single flight, it will generate around 7 terabytes of data, and there are like thousands of flights every day, probably hundreds of thousands of flights every day. So let's talk about, okay, so there's a ton of data, right? Now, when people talk about big data, what exactly is big data? The 3 key characteristics are shown on the slide, the 3 V's. Now, people have added more V's over a period of time. There are like 4 or 5 V's now, but I want to focus on the 3 V's today. First one is volume, by which I mean the scale of data. So a lot of companies are collecting terabytes of data every day, actually. And some of the big ones, like the ones that I've shown here, Google, for example, has 15 plus exabytes of data. Facebook has 2 plus exabytes of data. And Yahoo actually has 600 petabytes just on one Hadoop cluster, and they have probably around 20 such clusters. The second V is the velocity, or the speed at which data is getting generated. So it's not like traditionally how business applications were generating. Today the data is getting generated at a much, much faster pace. So the other name that a lot of times people will use is, in addition to big data, is fast data. And I've shown some examples here. So on WhatsApp, for example, there are 21 million messages every minute. On Facebook, there are 5 million likes every minute. The third way of big data is variety. So traditionally, most of the data that was getting generated was structured data that was stored in a relational database. That's not the case anymore, actually. Most of the data that's getting generated today is either unstructured or multi-structured data. So you can't really use traditional tools to process that. So big data comes with big challenges, and I've shown the two of the key challenges. One is storage, the other is processing, and we'll talk a little bit more about each of these challenges. So the storage challenge is that traditionally organizations use SAN or NAS devices to store data, but unfortunately these are expensive devices. So if you are storing like petabytes of data on these devices, it will get very, very expensive. The other issue is what kind of software you use to store that data, right? So they're basically either you store them as files or you store them in some kind of databases. Now traditionally people use a relational database like MySQL, Postgres, or Oracle, or SQL Server. But those databases were not designed to handle this kind of data. They can't handle the 3 V's of big data. So that's the storage challenge. The next challenge is processing. How do you process all this data, right? When you're generating terabytes of data every day, how do you process that? One issue is the processing needs are a lot more diverse today than they used to be, right? So traditionally, most of the data was basically put into a database and people were analyzing them using traditional SQL statements. So basically the usage was BI or BI basically, or traditional analytics. But today, most of the needs are beyond this, what you can do with SQL. The other issue is we want to be able to process that data in a reasonable amount of time. Now, the definition of reasonable amount of time depends on the application. For some applications, it could be minutes. For some applications, it could be hours. And I've shown 2 examples here, right? So, for example, if you're building an e-commerce fraud detection application, you want to be able to detect whether the transaction is fraudulent or not within seconds, right? You can't take minutes or hours, because if you do that, it's already too late. On the other hand, if you're building an application that's detecting fraudulent insurance claim, there you have a lot more time actually, right? So you could take hours, that's fine. So how much data can a standard server process today? It depends. It depends on the definition of standard server. It also depends what's the reasonable what's your definition of reasonable amount of time. So what's standard today was probably a very high-end server a few years ago, and what's high-end today is going to be probably standard in a few years, right? As with Moore's law, hardware becomes cheaper and cheaper as time goes on. The other thing is, so let's say a few years ago, right, 10 years ago, 100 GB would have been probably too much to handle in one server. But today, most likely, for most applications, 100 GB is probably not a big deal. You can handle it on one server, right? But as you start moving towards on your left, it becomes harder and harder. So what do you do, right? If you have terabytes of data or hundreds of terabytes of data that you want to process on a daily basis, what do? You have 2 options. One is you can scale up, the other is scale out. So let's look into look in more detail each of these options. In a scale-up architecture, basically what you do is you buy powerful high-end servers. So these are servers, for example, that may have hundreds of cores or maybe 200 cores in just one machine. Similarly, they have a lot more memory. So there are some high-end servers that can give you up to 10 terabyte of memory in just one box. And they are basically architected for high performance. But scale-up architecture has its own disadvantages. The first one is that generally these are hardware machines that have proprietary architecture, and as a result, they are very expensive. Not everybody can afford them. And the other issue is even if you could afford them, they still provide only limited scalability, right? So even if you have 10 terabyte of memory in a single box, what if you have hundreds of terabytes of data that you want to process? Still, you can't do it with one box. So the other option is scale-out architecture. In a scale-out architecture, what you do is you basically put together a cluster of computers to build one virtual supercomputer. So you're pulling together the compute resources that's available on each node, which is basically the CPU, the memory, and the storage, and you build a powerful computer using that. And scale-out architecture provides a couple of benefits. One is that it's relatively inexpensive. So for the same processing horsepower that you can get from a scale-up architecture, you can get it from a scale-out architecture at a much lower cost. So that's one benefit. The other benefit is that it allows you to scale. Basically, it's economical to scale. So you can start with a 3-node cluster, which doesn't require a huge upfront investment. right? So in the scale-up architecture, to buy one of those powerful boxes, you'd have to immediately make an investment of hundreds of thousands of dollars, which not everybody can afford. Whereas with this architecture, you could start with a small 3-node cluster, which may not cost you more than $5,000. And as your need grows, you basically keep adding more and more nodes, and then you have more horsepower to process that data as well as store that data. However, scale-out architecture also has its own some challenges. The first challenge is that how do you write applications that can take advantage of this distributed architecture? So you need to be able to take advantage of the CPU that's distributed, the storage that's distributed, and not everybody can do that. It's a very tough problem. It takes a lot of time to build this. Basically, you need to be able to, in your application, chunk out the jobs, right? Take your job, build it into small pieces, ship it out to all these different nodes, and then coordinate who's done, who's not done, and when they're done, we bring the result back. You also need to be able to handle the failures, because nodes do crash, hard disk crashes, sometimes there might be network issues, so you need to be able to handle all those things. The other issue is that typically, when you write program that's running on a single server, the probability of that node having some hardware issues is very, very low, typically less than 1%. But when you put hundreds of these nodes in a cluster, the probability of any one node failing is pretty high, which means you do have to tackle that in your application. All right, so let's talk about one of these solution technologies that was built to basically, that allows you to use scale-out architecture, as well as at the same time it addresses some of the challenges that we just discussed. So what exactly is Spark? It's basically a fast, easy to use, general purpose framework for processing large data sets using a cluster of servers. So in other words, it's basically allowing you to implement scale-out architecture, but at the same time it's making it really easy to use. And it provides a very easy to use, actually a very fast framework that you can use for a variety of different data processing needs. And we'll go into more depth into each of those areas. So the first thing it gives you is it abstracts distributed computing. Now, as a programmer, as a developer, you don't have to worry about, okay, how do I ship my job to different nodes? Spark is taking care of that for you, actually. It hides all the messy details of distributed computing for you. You have to just focus on the business logic that you want to implement. The other good thing is you write code, and the same code, exact same code, works either on a single laptop, and you can then, once you are satisfied that, okay, it works, you got the logic right, you can then deploy it on a cluster which has hundreds of nodes, and it will exactly the same. You don't have to make any code changes. The other good thing is it's highly scalable, so you could have a cluster of, let's say, 3 nodes, and the same code, you can then deploy it on 1,000 nodes, and automatically your code will scale because of all the things that Spark provides to you. It's fault tolerant, so even if, let's say, you have 1,000 node cluster, few nodes crash, you don't have to worry about that in your applications. Spark is handling it for you. The next thing is fast. It's extremely fast, and the reason I've coded them in a different color is just to differentiate Spark against Hadoop MapReduce. So prior to Spark, a lot of people were using Hadoop MapReduce. Now, MapReduce also basically provides these first 3 things. Abstract distributed computing, it's scalable, it's fault tolerant. Where Spark really shines is these 3 things. It's fast, much, much faster than MapReduce. It's easy to use, and it's flexible. So let's talk about the speed angle first, right? So if your data can fit in memory, Spark can be up to 100 times faster than Hadoop MapReduce. But even if your data does not fit in memory, it can be still 10 times faster. And I've shown a benchmark here that was done a long time ago, actually. Basically, they ran a machine learning algorithm called logistic regression on both using Hadoop MapReduce and Spark. And as you can see, it took only less than a second on Spark, whereas on Hadoop, it took almost 110 seconds. So why exactly is it fast? A lot of people ask me that. 2 reasons. One is that it allows applications to cache data in memory, and that gives you some speed advantage. But the other benefit, the other reason it's fast is this job execution engine. It has a much, much better job execution engine than what Hadoop MapReduce provides to you. Let's talk about the second thing that differentiates Spark against Hadoop MapReduce. It's much, much easier to use. So basically, as an application developer, you use Spark as a library, and it supports 4 different languages. It supports Scala, it supports Java, Python, and R. And then the core API, which was the RDD API, had almost like 80 plus operators compared to the 2 operators that MapReduce provides. Now this is kind of becoming more like the low-level API, and with the newer versions, probably you may not have a need to use that. you'll probably use this dataset or the data frame API, which is a much higher level abstraction, makes it even easier compared to the RDE API, which was itself a lot easier than MapReduce. It also provides a SQL interface. So if you don't like Scala, Java, Python, R, great, no problem. You can just do all the data analysis using just SQL. It comes with a couple of interactive development tools, which again makes it easy to try out different things in an interactive environment. So it comes with a Spark shell that's basically built on the Scala shell. And there are also a couple of notebooks that you can use if you are coming from the Python background and you're used to using notebooks. The next thing I want to talk about is flexibility, right? So Spark is basically not just meant for batch analytics of data. You can use it for a variety of different data analytics. So you can use it for, it comes with a couple of libraries. So there's Spark SQL, Spark Streaming, MLlib, and Graphics. These are the 4 main libraries that come with Spark. And you can use this to basically do not only batch analytics, but interactive analytics for machine learning, for graph analytics, and for interactive analytics as well. So one thing to keep in mind is the Spark is basically a pure compute engine. It does not have its own built-in storage. So sometimes people confuse it that, okay, can I replace my relational database with Spark? Not really, actually, because typically a relational database has both a compute engine or the SQL execution engine as well as a storage engine. Spark does not have a built-in storage engine. So there's one benefit of that is that actually you don't need to import data from other systems. So if you already have data in some other system, you don't have to import it into Spark. Actually, you can process from Spark data from wherever it is directly. The other benefit is that you can actually scale your compute nodes independent of your storage nodes, right? So you don't have to have take into account, okay, how much data I have and how much disk I need, and based on that calculate how many Spark nodes you want. You can just have Spark nodes based on how much compute processing you need, how much compute power you need. All right, so the good thing is Spark can process data from a variety of sources, and I've grouped them into 3 categories. The first one is basically distributed file system, so it supports HDFS as well as Amazon S3. And on these file system, it supports a variety of file formats. So your data could be in Avro format or Parquet or CSV or JSON. The next box is basically the NoSQL data stores. So if you're using one of these modern NoSQL data stores like Cassandra or HBase or Elasticsearch, again, you can analyze that data using Spark. There's no need to import that data from that data store into Spark. The third category is the traditional relational databases. So again, any database that provides JDBC connectivity, you can process data from that database using Spark. All right, so this is the last slide. So what is Spark really ideal for, right? What kind of applications really benefit from Spark? So there are three classes of application. The first one is applications that have a really complex data processing pipeline. So typically in the Hadoop world, MapReduce world, right? If you have a complex processing pipeline, you have to write multiple jobs, and you have to synchronize those jobs, and the data gets written into disk after every job. So there's like write and then read, write and read, and you have to synchronize all that. With Spark, you don't have to do that, right? Pretty much one job can have any number of stages, and so you're not paying that penalty of having to write to disk at the end of every job. So really, Spark is very, very good for those kind of use cases. The other useful class of applications for Spark is applications that use iterative algorithms. And I've shown 2 examples here. So there are like machine learning, for example. In a typical machine learning application, you make sometimes 10 passes over the same data, or even 100 passes over the same data. So if you have to do that, right, where you're kind of iterating over the same data again and again, that's where Spark is really, really good. Actually, you'll see a lot of performance benefit for those kind of applications. The third is ad hoc analytics. So again, since Spark is fast, right? Given the fact that it's Spark and fast and it gives you interactive development environment, if you want to do interactive analysis, Spark is very useful for that. Actually, you can analyze large amount of data. So typically, what will happen is, let's say if you're analyzing terabyte of data, right? The first time you issue your query, it will be slow because it has to read that data from disk. But then you can cache that data in memory, and once it's cached, all your subsequent queries will run much, much, much faster. All right, so that's a quick overview of big data and Spark. I don't know if you have any time left. So I can take one question.
Maybe one question, yeah.
Okay.
No, nobody.
Okay. Is there anything with Spark R and Spark 2.0?
I'm sorry?
Are
Have you done anything with Spark R in version 2.0?
What
Greater.
What do you mean by, well, I'm familiar with it, but have I personally used Spark R with 2.0?
Yeah.
Is that the question? No, I haven't used. I'm more on the Scala side, so pretty much everything I do is with Scala.
Thanks. Thanks, Mohammed. This was very informative. Hey guys, we're